I was interrupted many times, so that's why I put the final touch this morning. Okay, so far we talked about discrete random variables. By discrete, we mean they only take values like 1 or 5 or 10 or 1500. Nothing in between. So now we're going to talk about continuous random variables that can be like 1.239 or 55.99. So these are continuous random variables. What is called PDF, it's the probability density function for a continuous random variable. What does it give? So let's start. Today is the 26th. So the probability density function, it gives probabilities. Of occurrence of outcomes or variables. It is a function. That's what it says. It's a function. I plug in something and I get an outcome or a result. So here's an example. We're going to put them side by side, two different examples, because we're going to talk about both of them today. So here is one example. This is horizontal. And here's another example. This is what it's called uniform. It's a uniform probability density function. This is bell-shaped. We're going to call it normal very soon. Okay, so what are the properties? I'm moving on to the next properties of the probability density function for continuous variables. So what are the properties here? First of all, this area, because it's connected to probability, the area must be 1. So the area under this graph as well must be 1. Number 1. Number 2, for the uniform distribution or the uniform variable or the uniform probability density function, they're all same thing. If I want to determine probabilities, so let's say I have the distance here, but let's say on the x-axis, I have, let's say, between 0 and 60 minutes. That's one of the problems that we're going to look at in the middle in a minute. So between 0 and 60 minutes, this is the x random variable can take values between 0 and 60. Well, what could this height be? As you see, it's uniform. No matter what I pick, I will get this number. I'll show an example in a minute. But what can this be? For the area to be 1. So I have 60 times what? 60 multiplied by what is 1? This is a rectangle. Base times height. 60 times what? Well, this must be 1 over 60, because only 60 times 1 over 60 will give us the area of 1. So keep that in mind. What about this one? The same idea. However, this is a normal random variable. It has the mean right here in the middle. And because it's bell-shaped, if you remember, we have the 68%, 95%, and 99.7% empirical rule here. Because it's bell-shaped. Okay, so first of all, the heights are basically the probability, the height here, or for any piece, right? However, if for a continuous random variable, if I want to determine right here, the probability for x to be, let's say, 10 minutes, the answer is 0 because there is no area. So if this is 10 and I'm only asked to determine this, right? So it has to be base times height, but there is no base. Base is, there is no width for one number. But if I want to determine the probability between 0 and 10, then I have to determine this area. And that is possible. Base, which is would be 10, times height, which is 1 over 60, so it's 1 over 6. Same thing here. If you say find the area for this, x equals 20, I'll say I can't. It's 0. But if you ask me to find this area, I'll show you a way of determining it. So if I want to find, for this example, the area x less than or just less than or equal to, or less than or equal to, then I will have this area. This area right here. And I'll show you how we determine it. Okay, that's what it represents. The area under the graph of a probability density function is two things. And I'm going to write them what they are, and then we'll look at the first example. Okay, so the area under a PDF, number 1 and number 2. It has two different interpretations. So for example, for this, what does this area represent? Two things. Number 1, and I'm going to put them in writing. Number 1, what is the probability that we will get a letter, let's say, between 0 and 10 minutes moving from now on? That's the probability. The probability is 1 over 6. If we randomly select something, what are the chances that they will be between 0 and 10? Same thing, 1 over 6. So the probability for an outcome in our example, let's say between 0 and 10, is given by the area under the PDF. Randomly selecting x between 0 and 10, the result is the same. It's the area under the graph. So we have two ways of explaining the same thing. And here's our first example. It's exactly the same thing with the uniform. So we are talking about here, we're not yet talking about the normal probability distribution. We're still talking about the uniform. Everything I mentioned before is valid for both. That's why I put them side by side. So let's look at the first example. Assume that the U.S. Postal Services is delivering a package to your front door and so on and so forth between 10 a.m. and 11 a.m. So if I want to discuss this particular time frame, which is an hour, I will just copy that in a minute right here. So between 0 and which is 10 a.m. and 11 a.m., but this is 60 minutes. So this is time in minutes. And the same figure that I have over there, I have the area must be 1 If this is 60, this must be 1 over 60, so the area equals 1. Okay. Let the random variable x represent the time from 10 a.m. when the delivery is supposed to take place. The delivery could be 10 a.m. or 0, 60. Okay. With all 1-minute intervals of time, such and such, equally likely. This is to say your package is just as likely to arrive between this and this as it is to arrive between 1040 and 1041. So the random variable x can be any value in the interval from 0 to 60. Because any two intervals of equal length between 0 and 60 inclusive are equally likely, the random variable x is said to follow a uniform probability distribution. Okay, so now let's pick. So let's say between 30 minutes and 45 minutes. I want to determine the probability that we get the package between 30 minutes and 45 minutes, between 10:30 and 10:45. All I have to do is determine this area. So base is 15 multiplied by height, which is 1 over 60. So 15 over 60 is, when we simplify, we get 4. 1 over 4 or 0.25. So what is the probability that we will get our package between 30 and 45 minutes? 25%. We can choose another. Let's say the probability, let's say between 10:15 and 10:50. So between 15 and 50, same thing, base times height. So 50 minus 15, that's the base, times the height, 1 over 60. So 50 minus 15 is, what is it, 35 divided by 60, and I have to simplify it. I'll simplify by 5 and I get 7, and by 5 and I get 12. So 7 divided by 12 is the probability that we get the packet between 10:15 and 10:50, because every moment has the same possible probability. So between 14 and 15, 1 over 60. Between 15 and 16, probability 1 over 60. And that's uniform. Same thing. That was our first example. Now we are moving on to, any questions for me, please? Anything, stop me. Is this okay? Do we need more examples with the uniform?
I had a question for the first one we did. So it's just 30 minus 45 technically?
Yes, exactly.
Okay.
Yes. So 30 minus 45, it's base. That's the distance here. So between 30 and 45, the base is 15, and the height is 1 over 60. So this rectangle, the area of this rectangle is base times height.
Okay.
And the base is 15, and the height is 1 over 60. I picked another example randomly. I said, what if we get the packet between 10:15 and 10:50? Again, I have to determine this area. I didn't put it in because of not laziness, but because I didn't want to have too many things here. But let me explain what this is. So this is the base, which is 50 minus 15, and the height is still 1 over 60. Because every minute we can get the packet, and that is equally likely over the interval between 0 and 60 or 10 a.m. and 11 a.m. Is that better?
That's perfect. Thank you so much.
Thank you. Okay, moving on. I'm on page 2 of this document. You don't have to print it out, but at least save it so you have it. Okay, we already talked about the normal curve, but there are some details that I want to mention here. And also the properties, they go together. So the normal curve is a bell-shaped curve. And we know that. I'm going to try to graph it as symmetric as possible. I can never make it perfect. Okay, so this is a bell-shaped curve. And the mean will be here, the median, and the mode. So moving forward, we're going to talk about the shape is a bell-shaped, but this is the normal curve. And it has some properties that you may have encountered in algebra or not. Something called inflection points. I don't think you did, because obviously this is a calculus topic. You don't have to memorize this. But the inflection point means when the graph of a function from opening down, all of a sudden at this point will open up, or vice versa. From opening up at this point, the function opens down. This is the point of inflection. This is a point of inflection. These are points of inflection. So what is this so special here? It's because, see, it opens up till a certain point, and then, oops, it opens down till a certain point, and then it opens up. These are the inflection points. So if the mean is mu, it happens that because of symmetry and because of other characteristics of the normal curve, these are exactly mu minus 1 sigma and mu plus 1 sigma. And from the empirical rule, we know that this will be 68%. What other properties we have here? Another property that I don't think you encountered is this line. It's called y equals 0. It's called a horizontal asymptote. Again, you don't need to memorize this. It's not part of this course. That's my opinion. What does this say? It says that as x decreases tremendously, the function gets closer and closer to 0 without touching it. Same thing on the other side. As x increases without bound, the function will get closer and closer to 0, closer and closer to 0. That's why this is a horizontal asymptote. Just to understand the graph. Okay, I just wanted to give a couple of examples of potential graphs.